Good evening and welcome to tonight's lecture. I'm George Kraw. Tonight we'll be hearing a fascinating lecture on building smarter and safer systems for AI, and unlocking AI potential for autonomous systems. Introducing our speaker tonight, Carlos Felice, will be Dean Alex Wolf from the Bascom School of Engineering. Alex, I'll turn it over to you.
Thank you, George. Thank you, Ray, for supporting this wonderful, wonderful lecture series. I want to thank the audience, of course, for coming out tonight, and for those who are watching on Zoom, I guess it is. I assume it's Zoom. We are going to be hearing from Professor Sanfelice shortly, and then we will, Ricardo and I will have a conversation over here. We'll discuss some things that he presented and maybe some things that he didn't present. And we will also look to you in the audience, whether here in person or online, to also engage in that conversation. So I also want to point out that we are going to have another distinguished professor speaking in this series in April, and that'll be Maggie Saif El Nasser. So look out for announcements for her talk. So Ricardo, I want to introduce Ricardo. Ricardo received his BS in electronics engineering from the Universidad de Mar del Plata in Buenos Aires, Argentina. I've had the pleasure of going to Buenos Aires. It's an incredible city. Just a beautiful, beautiful, beautiful place on a really, really interesting river, the La Plata. He went on to complete his MS and PhD degrees at UC Santa Barbara. So he is a dyed-in-the-wool UC person. He held postdoctoral positions at MIT, as well as in Paris. His first actual faculty position was in the Department of Aerospace and Mechanical Engineering at the University of Arizona. And then we were able to, let's say, tempt Ricardo to come to beautiful Santa Cruz and join the Bascom School of Engineering in 2014, where he is currently a professor, but he's also chair of the Electrical and Computer Engineering Department. Ricardo's received numerous awards and recognitions for his work, including an NSF Career Award given to promising young scientists, the Air Force Young Investigator Research Award. The Air Force also recognized his promise. 2020 Test of Time Award from Hybrid Systems Computation and Control Conference. That's the kind of award that recognizes long-term impact on the field. So tonight, Ricardo is going to talk about some recent advances in hybrid systems and control, and he will explain what a hybrid system is. They're helping address uncertainties that are inherent in some of the most exciting technologies that are currently being developed today, and Ricardo will also talk about some of those applications. This research is broadly applicable, a range of technologies, including self-driving cars, air taxis, and even breakthroughs in healthcare. So the work that Ricardo will present tonight involves combining what are called certifiable algorithms with modern AI technologies. And the idea here is to create safer and more reliable vehicles and AI tools. One might ask whether injecting AI into these systems is actually increasing or decreasing their safety. And that's a question that I think Ricardo is going to try to address. So please welcome Ricardo.
Thank you, Dean Wolf, for the great introduction, and thank you for the invitation. It's a pleasure to be here. It's an honor to be here. I've been very much following the lectures, and I never thought I would get invited. And you never know, what happens when you're just looking around and doing, I would say, exciting work with the students, and I'll tell you about that in a moment. But as Alex mentioned, I'm very passionate about what we call autonomy in general, and one of the things that I've been working on, trying to understand what's the role of the emerging or resurrecting technology, I would call it, on AI. What is AI? What does it play a role for autonomy? So it's not a typical lecture, the one I want to give you, but I wanted to kind of pinpoint some very important concepts that I think some of you might probably know, but some of you will probably go home and say, oh, well, maybe I'll learn something new. And maybe we get into the hybrid systems and the mathematics behind this that I really love, but that will be a long night, I guess. But I want to start with something that this is the topic I wanted to talk about, the role of AI in autonomy, right? And I asked this question to ChatGPT. I said, give me a picture of the role of AI on autonomy. And if you didn't know that ChatGPT can draw for you, this is a pretty nice picture where you see Alex mentioned self-driving vehicles. That was the prompt. Give me the role. Self-driving vehicles, you can see some drones moving around. You can see something in space, maybe Mars, right? And the future is very exciting, right? Because now we have this technology that we know we can use. We have these phones. We have this power for computing. We have this reliability, to some extent, maybe dangerously, to the interconnected network systems, the internet and the such. How can we exploit this? And how can we use it with power systems, with communication systems, with safety critical systems to create these emerging technologies that probably you will be using in the near future. So I wanted to start with this question, and I don't want to go around and ask the question, but give it a minute. What is in your mind AI? Okay, it's a very perhaps hype type title or name, right? But what is AI? What do you imagine, right? Maybe just visualize it about AI. AI being artificial intelligence, right? All right. Okay, so there are many ways to define this, and I'm intrigued by this. I'm not an expert on AI, but I understand the basics of it, and I would like to tell you a little bit about, from my viewpoint, what really is. So one way to define this is that AI is the ability for computers to do some tasks, in particular, to make decisions like humans typically do, right? So that's kind of the intention. It's like you have this, let's call it data, and now with the data, you will give it to something, we'll call it system, which is this AI, and it's going to make a decision for you, okay? So for this, we need to use some sort of math. We need to understand how the logic between implications of if this happens, that might happen, whether this is realistic or not. So we need to use physics rules and to understand kind of the reality of where we are, right? You probably learned or heard about machine learning, right? ML, machine learning. Machine learning is actually a way to learn behavioral, recurrent behavior or patterns using data, okay? So the idea is that I get data, so I measure, let's say, temperature of my house, and I measure temperature throughout the whole year, and then I can build essentially a pattern of my temperature in my house, right? And based on that, maybe I can schedule how my heating or cooling system, whatever you might have, should be actually performed, right? Now, there is another term you probably heard, and that's in the Valley is very hot these days, which is called deep learning, right? Or deep neural networks. And maybe we heard about this, and we don't understand the details. I want to give you a little bit of that, and a little bit of those concepts. These are more complex. They're deep, okay? In some sense, and the question is how deep, right? And what does it mean to be deep? And what happens if it is not deep, right? So that's more complex ML, at least for now for us, okay? All right, so those are two things I wanted to mention. Now, machine learning, deep learning, and other things that I'm going to mention is not all AI, right? It's not all of AI. There are more things than AI, okay? And this is a nice pictorial description of what AI really is. Certainly something that runs on some sort of computing microchip, right? Something that is digital and is being designed with circuit laws, right? Very foundational theories. and involves machine learning, as I see there at the top, and deep learning as well. But then you also have natural language processing, because it's important to understand how the data translate into real standard ways to communicate. Another way that you can relate machine learning and deep learning is via vision, right? We probably heard that you can use images and learn from images what the images have, right? So that's another data point. And the other aspects. And one of the ones that is very important is the aspect of neural networks. So how many of you, by raising your hand, have heard of a neural network before? All right, so more than I thought. Very good. So what a neural network is nothing more than a description of a function, okay? So I'm gonna get into those details in a moment. Here is a neural network, okay? It turns out that all of, I would say the majority, but maybe all of the AI achievements have this thing in common, which is an artificial neural network, okay? So this is the entity that actually will create your decision making, all right? The way we read this is from the left, we think about data that we provide, and to the right, we see as decisions or output that we obtain from the data. And you can think about this as channels, right? You get data, you get this, let's say, temperature, measurements of temperature, and now I pass them through this, and it's gonna tell me at the end, with some logic that is involved in the network, it's gonna tell me, you should turn on your heater, or you should turn off your heater, okay? So this is a pictorial description of a network, and there is something called an input, there is something called an output, and there's something called hidden layers. And the difference between a standard, or what we call a shallow neural network, and a deep neural network is that the deep neural network is going to have a lot of these levels in purple, okay? If you have one or two of these levels, it will be a shallow network. If you have many of these, you will have a deep neural network. So that's, I guess, demystifying the difference between neural networks and deep neural networks. Nothing more than adding more labels or layers or more buckets to fill in with data, right? Now, you're going to see that these are not just a few buckets, they're a huge number of buckets. And what happens is the following. Why would you use, or how would you use this idea of neural networks, all right? So here's an idea. And this is all behind a very, I would say, deep, not necessarily pun intended on the deep neural network, but it's a kind of deep result, which is called the universal approximation theorem. We're not going to go into that, but the idea is basically behind this. Suppose that I have an unknown relationship, okay? A relationship is what I will call a function, but just think about something, a relationship. Like, for instance, let's say, as I was saying earlier, throughout the day, let's say I look at the temperature and I measure the time at which I look at the temperature. So I build a relationship between the hour right now and the temperature. And maybe I do that until I hit the maximum of temperature, right? So that's a relationship, yeah? And I can measure this, right? I have a thermostat, or I have a thermometer, or something of that sort, and I can log this data. All right. Another relationship will be the slope and speed. Okay, so if you're going down the hill on your car, on your vehicle, or your bicycle, or even running, then you could probably create an increase of the speed as the slope gets higher, right? If you're going down, or if you're skiing, right? This is fun. All right, another one is somebody once told me, no matter how much money you make, you're gonna always spend more, right? So that happens, right? It's the nature of, the resources, right? So that's how the relationship might look like, okay? So what you do in learning or in AI, what you try to do is to collect this data in order to obtain a mathematical description of this relationship. Okay, so back to the temperature, which is probably the simplest, I would like to come up with a way to describe this curve. All right? And the way you do that, and this is, I promise you, this is my only equation on my talk. I was advised not to put many equations, is that you would like that relationship, call it this Greek letter phi, is essentially relating my inputs, which are these x's, to the output. And then this little n right here in the sum is the number of network or the number of neural networks that I have, or layers as well, okay? And this little piece here is the neural network. As you can see, it's just a product and a subtraction, or a sum, depends on the sign of the coefficients. But what is very critical here is this little function there, or this little extra relationship, which is what is called the activation function, okay? So the craft of the AI expert, which is not me, is to figure out essentially how many ends do I have, and which sigma do I pick, which is another relationship, and which coefficients do I pick, okay? To relate my input data to my output data. So that's the question. Call it a fitting question. Linear regression, anybody? Linear regression? Something like that. Not necessarily linear because of that sigma. So if you think about ChatGPT, let's say 3.0, which is a cheap one available. Actually, you can get 4.0 available for free. Can you guess how many of these relationships, or how many neural networks you need? How many layers? Billions. So you have billions, okay? And why billions? Well, because the universal approximation theorem says that if I have a relationship, time to temperature, there exists, and that relationship is somewhat smooth, there exists a neural network that will approximate it with arbitrary precision. So what happens is that it's essentially telling you, if you find enough data and you try to search in the space of relationship sigma and the weights W a fit, then you will find it, okay? So that's the magic behind ChatGPT, the Google version, the Apple version, and so on. So let's get a little bit probably more realistic, because in theory, these things can approximate any relationship or any mapping, but we are not going to get into those details right now. But think about how you use AI these days, right? So there is one nice example, which is what I really like, which is this voice assistant, right? Probably all of you take advantage of that, especially when you're driving. What's the input of my neural network? The input is a phrase, right? I give you a phrase, like for instance, what's the weather today? And then what I would like to have is an output, which is a response that says, well, today the forecast is going to be beautiful, like in California all the time, sunny with a high of 75 degrees, okay? I'm actually giving a talk about this in Iceland in the summer. It will be interesting relationship to this. But anyhow, how this works is that the neural network learns to map the audio waveforms, which is the input, to text, and meaning, which is the output, okay? And then provides a relevant response. So it translates text into binary objects. It builds the network weights. It picks a sigma or an activation function, and then it gives you this relationship. And that takes months to train, okay? And as I was saying, trillions, billions, and maybe more data points, okay? Now, for text, it's not that difficult because you can throw a lot of books, a lot of online material. You can send a lot of stuff, and then it will figure out things like something that you probably don't want to be bugged with, but maybe shopping recommendations as you are going around, right? Or maybe movies recommendations, or maybe something that you can do here. I think I skipped one. Where is it? Okay. I had the other one, which is the text suggestions, which is very useful, right? When you're writing a text or an email, it tells you what you could have next. That's pretty convenient, right? So how does it know that? Well, because it has figured out that after, my house is, I have all these possibilities, and then if I start writing a word, I write first a letter, and then it narrows down to all the possibilities, and then it keeps going, narrowing down, and eventually will give you 3 top options that one of them will be a good option, right? So then you take advantage of that. So that's, again, what's behind. So now you can go home and say, well, the AI is running my data through this object or this neural network with multiple millions, billions of channels. And then the question is, how fast can one do that, right? So there are different type of networks. There is convolutional neural networks. There are, low short-term memory. There are different variations of these where the networks or the links are totally probably biased or changed to actually learn things properly. For images, convolutional neural networks. For text, also convolutional neural networks or long-term memory. And again, you can build from there. So back to this question. Now that we understand a little bit about what AI can do for us, how can we use this for, let's say, designing more reliable and safe, and I would say high-performance systems, right? That's very important. How do we do that? Well, the things that come to mind to me is that if I can have these systems, think about these as sensors, right, that move around the environment. If I can have these sensors collect data for me and tell me more information that I currently have about the environment, that's great, right? I just need to build a neural network that will give me the information about the environment in a more realistic manner, and then I can decide how to move these vehicles without hitting what's around, right? So that's a good idea, and that's what we can do. That's the core idea of autonomy, is to actually solve problems with minimal or no intervention of humans. For that, you need to have an algorithm that will actually tell the, let's say, the vehicle what to do, right? That's critical. All right, so here's my suggested example to understand and to kind of discuss a little bit autonomy. Because I know that most of us probably interacted with this, or at least didn't want to interact with it and try to turn it off, right, in the car. Either one. So if you're driving long distances, right, you probably take advantage of what is called cruise control. So the simplest form of cruise control will only do the speed control, okay? So you turn the desired speed, let's say 65 miles per hour, you are in a 65 mile per hour road, that's what you should be doing, and now you just cruise. So if you're at low speed, it's gonna crank the speed to 65, if it's a high speed, it's gonna go down to 65, okay? So you have a profile of velocity that will converge to what we call the desired steady state, all right? Now, if you have more fancy cruise control, which is what is called adaptive cruise control, now what you can do also is to measure the distance to the vehicle in front of you. And in addition to controlling the speed, you should also control the separation, which you don't set. You can set that, right? That's hard-coded into the system. However, if you want to figure out how to set it up, let me know. Send me an email and we'll play with that. But certainly you can now, if you're going 65 miles per hour, that's your goal, and this car in front of you in your lane, and you want to stay on that lane, is going 55, you better slow down. So that removes a lot of the weight from the driver to keep this safe separation, right? And actually, these separations are well documented. They're designed for safety based on regulations, okay? Very good. So you have what is called a system of two cars in the advanced cruise control, where one is measuring the speed of the other, and then is adjusting their speed and their throttle and their brake. So you have a system here that has, if you're just moving on a straight lane, is controlled by throttle and brake, right? That's your control input. That's what we call control input. Your measurement is your distance and your velocity, okay? And more recently, you probably realized that you can also latch to a vehicle in front of you in the advanced cruise control. So they use imagery, so they use vision control to figure out which object should I latch to, okay? And it's interesting because sometimes you have a big truck in front of you, and it should do something different than you have a motorcycle in front of you. So give it a try. It's a pretty interesting system. Now, what these systems do is actually using what we call feedback. And this is a empty, correct slide. There's typically something inside those blocks. I'm not going to get into those details, but what happens is that we measure speed or distance, and we use that speed or measurement to feed it back into my decision, okay? So if I'm about to get too close to the vehicle in front of me, and I'm going at 65 miles per hour, and the vehicle in front of me is slower, then I need to slow down, right? So I need to tell my throttle or my brake to actually apply the right pressure in order to create a slower speed to maintain my distance, okay? But this is the idea. The idea is feedback. And actually, I will argue, it's hard to prove, that every system we interact with has feedback, right? Every system, even the very fact of walking, because you are contacting the ground. If you don't have anything in front of you, you will probably realize that you need feedback. in order to do that task. So feedback is fascinating, and it's also mathematically interesting because now you're bringing back these arrows and this information back into your system. So what is feedback control in autonomy? Well, feedback control monitors this output and adjusts the inputs, okay? As I said, brake, throttle, those are my inputs, and based on the speed or distance, I will adjust those. And it will do it autonomously. That's pretty fascinating and very nice, right? Now, how do you design these systems? Because it's not easy to figure out what to put in here, especially on the feedback part, right? What should I do? Multiply, divide, subtract? So there's a theory behind it that is called control theory that will allow you to actually mathematically design how to do the correction. Okay? So that's what control theory does. And there are a few notions. One of them is stability, because I don't know how many of you have, that's probably, I don't want to get into car accidents, but how many of you have flown a plane? Okay. All right, very good. So one thing that you realize when you fly a plane is that you have to control many things, okay? So you have your rudder, you have your aileron, you have your elevator, you have your throttle, and everything is, 4 knobs. You have 4 knobs. So how do you do that? Well, you practice, you practice, you practice. So how you control a system with 4 inputs? That's difficult, right? For a human, it's difficult, and that's why we take 50, 100 hours of training before we can tell somebody that they can fly on their own, right? And so on. So that's difficult. Imagine doing that autonomously. That would be fascinating. It actually, the technology exists. That's how we fly commercial jetliners these days. But you need to have some sort of theory behind it to actually design this, not by trial and error, because as you probably realize, you have 4 knobs. If you put wrong rudder or too much elevator, then you're going to probably get into a stall condition, right? So, and the example that I mentioned earlier has a feedback nature of signals, very clear. You want to maintain a particular output. You want to control your input, as I said, brake and throttle. And I think that's clear for now. Now, the question that it might come up to you is, why not just use AI to do all this, right? Why not just let the AI? And maybe you can answer the question right now, because what I told you what AI can do for us is feed or complete the neural network parameters. And how I'm going to do that, right? I mean, if it has 1 billion of nodes and 1 billion of weights, and how do I do that? And how do I prove that's going to work? So once you realize of the basic concepts of AI that I mentioned to you, you realize, well, this is not going to be my desired way to fly autonomously, right? Perhaps. Because AI-based algorithms, they just don't have guarantees, don't have what we call formal or, to be precise, mathematical guarantees. Okay, because we don't know what the weights are until we run the experiments, which are many, many experiments. And learning-based models will essentially not see all the edge cases. The same happens with control theory to some extent, but edge cases are difficult because your network is what we call trained, which means these weights and these functions are chosen based on the data that I receive. If in my data I don't have an edge case, a very complex situation that I don't happen often, right? I don't know what to do with it, then it's not going to be part of your network. And then when that data enters into your network, you won't be able to create the right decision, okay? So you are making decisions only with the data that you know. You can't expect that the network is going to come up with its own good decision. It might happen, it might not happen. So that's the lack of formal guarantees. And those are critical. On the other hand, and again, these are not very deep, but now I fill in a little bit on the feedback system. If we have a model of the process I want to control, I can come up with a model of my feedback component. So that's the G and the H respectively. And when everything is linear, which is not always the case, but it's important, control theory have very nice design techniques to guarantee that the system has stability, performance, safety, and so on. So that's the good news of control theory, okay? The catch is, or in my opinion, the advance here is, how can I use the learning benefits from AI to do this control design theoretically provable better, okay? So here I want to just very quickly, as I said, stability guarantees are good in control theory, not in AI. Some networks might behave unpredictable under certain edge cases, right? As I was saying, unseen conditions. Robustness is something that comes from the design of the control theoretical algorithm. But AI will not probably do well if they haven't seen those conditions. And last but not least, safety, which is critical. You can actually design using control theory systems that are safety critical, but AI algorithms are difficult to certify for safety due again to the unpredictability of the system because of lack of guarantees. So I wanted to kind of spend the next 5 minutes on what I would like to say is an opportunity here, because I do find a lot of benefit in being able to come up with an algorithm that not only creates feedback, but also learns as it goes and figures out what to do, right? And that will be nice for autonomous systems. So are there any clear kind of synergies here? I would say yes. So AI can do that learning. Control theory can actually create this formal framework. And if we combine those two, perhaps we can get into intelligent systems that are reliable and robust. So, and I have a very simple, but I would say illuminating example here. And imagine that you have a drone and you want to have the drone to follow a particular path, a circular path, to just take imagery on whatever you're doing below the drone, right? And that's the path that you want to describe. But all of a sudden, what you have, unavoidably, is wind. So you're flying outdoors, there is wind, and maybe you don't know what the wind is doing, and maybe you want to learn it as you go, okay? So I'm going to throw in this into the control theory paradigm, okay, which is there. So this is my 2 blocks with a little more detail, which I'm not going to get into. But what happens here is I have a control algorithm that is called proportional integral derivative. It's a linear type of controller. And I have my desire of following that path. So my desired path is this blue circle. And the system I'm controlling, or the person I'm controlling, is this drone, okay? And there is feedback here. But what I'm going to add is, in addition to the traditional control algorithm, I'm going to augment my control action with what we call a neural network controller, okay? So what I'm going to do is to run experiments for multiple type of controllers that we know in the literature might work for situations with wind type disturbances, and I'm going to run one with my new algorithm, with the neural network, okay? So what you see right here is a 2x2 grid. Top left is the traditional control scheme that we learn in our undergraduate control theory course. And the top right and the bottom left are more advanced. These are adaptive controllers, okay? And what you see at the very bottom right is our new controller with learning. And the circles are the circles you want to follow. The drone starts from the middle, okay? And we can launch the experiment. The wind comes from the right. Same setup. This fan creates the wind, okay? And now we are going to run this. So there it goes. That's the experiment. The drones essentially start taking off. And then once they are at a particular good altitude, they're going to start moving and trying to follow this blue desired path, okay? And as you see right away, is that the traditional control design struggles mightily, right? I mean, the wind is really kicking it and getting it out of the path. The adaptive one right here is a little better. The dynamic adaptive is much better, but the neural network in the loop correcting is so much better, right? So much better. Again, this is not a mathematical proof because it's just one instance of an experiment. But essentially, if you look at these trajectories here over the run, the AI with feedback control is actually doing something pretty good, right? And the reason is because, or one reason is because the wind coming from the side, it doesn't always hit the wind, the vehicle on the same side, because the vehicle is going to go around, right? Okay. Now, if I put a model of the vehicle there that's going to go around, maybe I can do better with the initial algorithm, the basic traditional algorithm, but then I can change the path and I can find another situation where it's not going to work. And this actually is pretty good and works quite well. So this gives us some hope that this idea of augmenting my system for control with some learning is actually a really good idea. Okay? So how to systematically do this? This is part of the current research. There is no complete answer to this. There is not a textbook about this yet, but we're working towards that. And the idea that we have been working on is to use what we call hybrid systems theory to be able to enable the combination of classical, advanced, control theoretical approaches with AI approaches, with these ideas of neural networks, okay? So hybrid systems are systems that involve discrete and continuous behavior. Like logic is one of those, physics is another one of those, and maybe a simple example, since I already talked about this, is I have my house and I have a sensor that takes the temperature, and then based on that, it decides whether you should turn on or off the heater, right? So is this a hybrid system? Well, I have a physical process, which is my temperature. It changes continuously over time. And then I have my heater that is going to go on or off according to a desired temperature that you would like to have, right? So imagine that my desired temperature is 68. That's what I like. That's my green temperature set point. What's going to happen is that my temperature is going to overshoot to 69, and then the heater is going to go off, and then the temperature is going to go down. It's going to go to 67, and then the heater is going to go on, and then it's going to keep happening, right? So I have, again, this continuous physical evolution of my temperature, and I have these switches on and off that is part of my overall system. So I can think about this as a combination of physics, or continuous, and discrete, or resets, right? And we're not going to get into the theory of this, but you can think about how this idea is very interesting. Imagine that you have a system with different modes of operation, like you see right here in this kind of automata type of system. And actually, this relates to autonomous aircraft, because you can think about Q1 being taking off, Q2 being level flight, and Q3 being landing. And you have 3 modes of operation for your system. And you transition between those, and that's actually how airplanes operate. But you can think about this in more mathematical sense, which look into these trajectories that have transitions and also continuous evolution. We wrote a lot about this in our 2 previous books on the theory behind this. So this is mathematically heavy on analysis of closed loop systems and then design of controllers for this type of systems. But one of the things that we are doing now is to bring this to the idea of combining control theory and learning, or AI, right? So I'm going to wrap it up with a couple of applications. One is back to the drone, right? So we have the drone, and now imagine I have an obstacle in front of it. And does anybody recognize that tree? The biggest tree in the world. Exactly. So imagine that you have that tree in front of you that you want to go around. So this is 25 feet wide, 250 feet tall. Okay, and then you want to take it to a landing pad for a drone, right? You're doing some sort of surveillance in the forest. Not that you should, because NPS would probably not like that. But then imagine that you look at it from the top, and you see that you want to get there, right? And you have your obstacle in front of you. So what would you do? I mean, would you go 250 feet high? Maybe not a good idea for getting on top of the wind up there. You can go around, right? You can go that way, or you can go that way. And if you run what is called reinforcement learning, which is an idea based on filling up the parameters of a neural network, you will actually come up with these solutions. All right, you're going to go around, left, or you're going to go right. And that's probably not a bad idea. But what happens is that once you start looking at this, you have the capability of creating a line behind the tree where you're going to go either towards the left or towards the right with the small variations of your location. And as soon as you do that, you realize that if I have a little bit of noise, I could be on the top of the line, and the noise tells me that I'm at the bottom. And instead of going towards the left, I go towards the right. And as soon as I do that, the noise, which is unavoidable, might tell me that I'm no longer at the bottom of the line, I'm on top of the line. So I should go left rather than right. And I keep chattering and going around that particular region. And if I have forward velocity, Gray Sherman won't be happy about that. So what happened now, if you can think about the multiple obstacle cases, and this becomes much more complex. And as you add noise, as you see right here, you have some sort of trajectories that get somewhat stacked. So what we did a come up with is what we call hysteresis reinforcement learning, which uses some sort of memory in order to actually create these safe paths to avoid this chattering behavior. So the idea is that if I decided to go left, I'm going to stick to left unless I get pushed too much down by perturbations or noise. And then if I decide to go right, I'll do the same. So we have an overlapping set of variations there. And we apply this to a pretty fascinating game called the capture the flag game, where you have your blue trajectory or your blue agent right there capturing the flag of the red and bringing it back home. And the way that it works is, see the red gets stuck there, is using this idea of the noise to actually prevent the red from catching the blue. So here's going to start again. See, they go stuck there. Okay, you go again. Red gets stuck, blue goes around, grabs the flag. It gets caught, but at least it grabs the flag. In this situation, it's going to grab the flag. And now it's going to create an avoidance. And you can keep playing this game with this hybrid approach called hysteresis RL. Now, another thing that we are doing is, because these neural networks, which could be now used to design controllers, meaning algorithms, they're also having this universal approximation theorem capability, which is they can approximate any function. So that's a very powerful thing. But again, as I said, there might be situations where these functions are not well capturing corner cases. So one thing that we decided to do with one of my students is, what if we have a reliable algorithm? We'll call that a certified algorithm. And now I have an AI algorithm which is not certified, but is probably very good in terms of performance. What if we try to use the AI as much as possible, but when things start going wrong, we switch and we use the certified algorithm, right? Makes sense? You exploit the AI controller as much as you can. When it becomes risky, you switch. All right, so that's another kind of situation where you have switches, you have possibility of turning off and turning on different algorithms on your system. Again, we're not going to get into the math, but the idea is that if I have a simple system on the plane, and this is my obstacle, I will try to use the AI as much as possible to get to 0, 0. And as you see right there, the AI didn't know about this obstacle. Okay, well, I use a certified one, and then the AI again, and then the certified one, and then the AI again, and then eventually I can use the AI all the way to take me to 0, 0, which is, again, a landing location for the drone, let's say, from a view from the very top. So that's the idea, and that's how you can actually switch between these algorithms, and that's what we're working right now. So there are a lot of applications. We have a project on space for space exploration with refueling and detowing and decommissioning of a spacecraft, and there is a lot of interaction between robotic manipulation for repairing the system. There is a source of uncertainty that can be captured with AI. We have another project that looks at how do you actually design these algorithms to guarantee that you don't spend too much time computing, because these algorithms might take a long time computing, especially for vision-based control systems like self-driving vehicles. And how do you guarantee this? And how you can use neural networks to actually overcome those limitations? We also have a project that is very relevant to our region, which is related to deploying autonomous vehicles, in particular air vehicles, to actually monitor and predict the future hazards due to fire. And you can imagine that the neural networks will be very important, combined with control theory, because you can predict in the future how these potential fires might emerge, okay? And then another project that we have is a recent project we started on berry picking. How do you actually identify which fruit is ready to be picked? And once you identify it, can you grab it in a manner that is not destroying the fruit? How do you identify it first? There is a lot of classification going on there, and then closing the loop with control, with force control, to grab the berry, as you see right there, and put it safely in one of your collecting systems. Now, all of the things that I show you wouldn't be possible with the work of many, many, many of my students. There are active students and postdocs right here, alumni right here, working with us on many of these problems and getting their degrees in fascinating topics. And Daniel, who is right there, is my current postdoc, can attest that they all work really hard and that we love what we do, and that's what we enjoyed. So with that, I wanted to wrap it up and just say that it's been a pleasure to give you an overview of what AI does from the point of view of control theory. How can it interact and work together with control theory, not replace it, complement it, come up with ways to solve problems better with the combination of the two. And I do think that the hybrid approaches that I've been mentioning are a very good way to move forward. And I hope that in a few years I can tell you more about what we have accomplished over the years. Some of the takeaway messages that you hopefully take home is what are neural networks, why wind is a problem, what is switching, right? And maybe what great German will tell you if you go to Sequoia National Park, which I highly recommend you. Anyhow, thank you for your attention, and I will be here to have a discussion with Alex for more questions.
Well, thank you very much, Ricardo. That was really interesting. It's always good for a dean to actually know what their faculty are doing. It helps. And you generated for me a lot of questions, and I'm sure in the audience as well. And I want to just start off by asking you a few questions. And then really, I would really like to invite you to ask some questions as well, or just make some comments from your own experiences. First thing I feel compelled to mention, by the way, is you talked about reinforcement learning. And I wanted to point out that today was an announcement of the Turing Award, the ACM Turing Award, which was made by Association for Computing Machinery. And it's an award that comes with a $1 million prize. And it was for two people who really are the parents of reinforcement learning, Andy Bartow and Rich Sutton. Just so happens that Rich Sutton and I were PhD students together. So this is the first colleague of mine, direct colleague of mine, who received the Turing Award, and that's a moment of pride for my institution. But yeah. So you're training to be a pilot, I understand. Is that right?
I'm learning. Yeah.
You're learning.
Training is a big word. Right?
Yeah, that's true. You're learning. Is there something about the work that you do that is helping you think about flying a plane as you're learning to fly a plane? I mean, do you think about yourself as a controller or as an AI?
Well, I mean, there is nothing better than interacting with a system or with whatever you want to get a problem solved on, right? So when we started this TaskFire project, we realized we need a lot of data. So we might as well fly ourselves, but we cannot fly all the time. If we have a pilot in the team, then we can actually do that all the time, right? So that's what I was like, I teach about these things, but I don't know how to actually fly a plane. I teach about vehicles, cars. I can drive a car, but one thing I realize is just so humbling that it's such a complex system. The car is a complex system, but it's not as complex, right? Because first you're on the ground, so your obstacles are pretty much in the back or in the front of you, or maybe on the side, but not laterally, or not above, or not below, right? Second is that you realize that you have a lot of controlling authority on the system. As I said, 4 actuators. We call them actuators, but inputs, right? Rudder, aileron, the elevator, and then the propeller, right? And some airplanes have more, which is just for fun, right? To make it difficult. But the idea here is, what I'm learning is, what's the difficulty of controlling this machine? And the way I approach it is like any other machine, right? Or call a cell phone or a computer, is trying to understand how I can make this system do what I want it to do. The catch compared to autonomous systems is that humans have so much sensory information that the machines don't have right now, and I would say maybe we'll never get to that level, right? I hope I'm wrong, but definitely learning to fly the plane with information that you have as a human is so much easier than doing it with a computer. Let me put it that way.
That's interesting because if you think about it, you take the plane up, you fly it around, and you land it. That, in a sense, is one learning iteration, right? But you're talking about training an AI that takes billions or trillions of learning exercises. You will probably have, maybe 1,000. So it's interesting to think about you as the controller learning this from 1,000 trials to an AI that needs billions or trillions of trials. How do I think about that?
Well, the instructor is the key, right? The AI doesn't have an instructor. It's typically, unless it's a guided learning, which is difficult, but the way we can do what ChatGPT does is because the problem is not easy, but it's somewhat easily to guide, right? It's like the text itself is the guidance. When you're flying a plane, if I wouldn't have the instructor, there's no way you can fly a plane, right? Easily. I mean, it will be okay for some people, but when you have the expert to the right and they tell you, well, you do this, you do that, you start looking at what they do first, so you have a model. So I would say your exploration space is narrow, is shortened to such a small space because it's just imitating the expert. And that's what makes it possible with 50, 100 hours of training to fly a plane. Let ChatGPT type approach fly a plane. It will take years, maybe more, right? Because in order to find the right combination of these multiple inputs to create takeoff, level flight, and landing safely, it will be just too big of a space for search of a solution. So that's my point, is if you have a guidance algorithm, if you have an expert system that you can follow that has accomplished the goal, then it's much easier to kind of converge to that versus trying to find it in this whole large space of options.
So when you build these controllers for drones, they're drones, right? They're pieces of equipment that are actually flying, that cost money. How do you train them? I mean, you can't just let them fly around arbitrarily and crash and do whatever they do because it's not practical, right?
Correct.
So what do you do?
So in one of my slides, I was showing the kind of the paradigm of control theory, right? And in that slide, essentially what you see right there, let's go to the simple one. There, the one on the top right, that one essentially what it relies on is on a mathematical description of the process of the system I want to control. So what we do as control theorists is we take a course on modeling. And that modeling course will allow me to say, okay, if I have my car and I apply this much gas, or this much brake, this is what's going to happen with my position and my velocity. So I build a mathematical model, and typically the model is using first principles, like Newton's laws, right? And then you build what is called a mathematical description of the system, typically done as a differential equation or a difference equation, depending on the framework, but that's more deep into the idea. But you have a mathematical model. Once you have a mathematical model, then what you can do is to use your design, which is called model-based design, to design the feedback part. And once I do that, I simulate that in a computer. So we have tools to actually do a simulation. More recently, physics-driven models have come up, and then you can actually test these in a model that is not your model, but is a model that some 3D generator tool, like SolidWorks, might probably has given you. And now you can test your design there, your control design there. And then when that crosses through, well, you can go and do hardware in the loop simulation, which is your hardware is going to interact with the software model and tell me whether my controller is going to perform well on my software model. And after you do those 3 stages or 4 stages, then you go and deploy, right? And if you were to do that with AI, to try to find a control algorithm then you'll need to do the same, maybe with a model, maybe without a model. So there is reinforcement learning with models and without models. Let's say you do with a model, then you need to do reinforcement learning with models, which takes, away the expertise of the control theorists, but it needs to find a solution, which might be possible or might be not. It all depends on how you tweak your problem. there's something called the reward function, which we didn't get into details, but if you do design the reward function properly, then you probably get to a solution. But if you don't, then you might not get a solution. So there is a challenge there on how to find a controller using a reinforcement learning type AI techniques to solve your problem. Or you can go outdoors or in the lab and do all these experiments. But as you imagine, you need to have multiple experiments. What I've seen some of my colleagues do is to actually have the drone, let's say, that you want to control, flown by an expert. Again, we're going back to guided learning. And now I have essentially this map that the expert has given me. So the expert will fly it for, let's say, a few hours, right? And you collect all that data, input, output data, what the expert did, why did they do this when that happened? So you can figure that out, and that's your training set for designing your controller. And in an ideal situation, because of the universal approximation theorem, then you will be able to come up with a neural network structure that will imitate what the actual expert did. So that's the shortest path to solve it using AI.
Any questions at the moment? Okay.
Would your control theory be useful in getting applying morals to AI? That's a type of control, right? Like don't kill people, stuff like that.
Right, and the structure that I show you at the very end, the structure where we monitor what AI is doing, right here. Right here. If I have the AI algorithm running in my system, let's say it's a drone, again, and if the AI is trying to get into a situation where it might not be ethically correct, then I could probably switch it off to a controller or an algorithm that will actually be ethically correct. Or in a better situation, I would say I will already design my AI, and that's what I would like to do if I were the designer, is design my AI controller to be morally, ethically correct. Which opens another question. How do you actually quantify the ethics of autonomy? That's a totally different talk. It's definitely not by me because I'm not an expert, but I'm trying to understand how do we incorporate those specifications, right? And what do those mean? Conveniently, there is a theory, an approach that allows you to synthesize these algorithms with high-level specifications. So imagine that you are a user of this tool that synthesizes these algorithms, and what you would like to do is take the drone around General Sherman to the landing pad. That's all you tell the system. And then it designs all your algorithms. But you can add to that, if there is a person on the way, stay this many feet away from the person, right? And you can keep adding kind of predicates into your design, and then the tool is supposed to give you a control algorithm that will actually satisfy all those specifications.
Yeah, so this is a question coming from Zoom. They're asking, in the context of AI systems learning from large amounts of data and then themselves generating data by interacting with the world. So namely generating text, books, algorithms that then are dumped into the internet and then become data for other AI systems. Do you have any concerns that these solutions then become self-fulfilling prophecies in the context of being really precise, to learn from a large amount of data, but that data may not be accurate because it came from another AI system? So,
that's a very important concern. Actually, if you go to, let's say, ChatGPT, I keep beating ChatGPT, but you could ask questions that you know the answers and it will give you wrong answers. And that's because online there is data that is correct and there is data that is incorrect. And the question is how you flag that. That's why it's such a risky tool, right? And it's not only a risky tool for the expert, but also for the novices. And I see that with young generations that use these tools in a situation that they don't know how to solve the problem. Like, let's say, writing an essay, right? You can write an essay out of ChatGPT, but I will only write that if I know how to write an essay, because then I can judge whether what the essay gave me is correct or not. But if I don't know how to write an essay and I use that as my answer, then how do I learn how to write an essay? So there is not only the source of, I would say, incorrect information that needs to be filtered out, who knows how, but also the abuse and risk of not being able to do what we can do now because the generation is changing based on what they use.
Well, it's interesting because, of course, that's a feedback loop, right? And so the question was actually talking about a kind of feedback loop in which the AI is training future AI. And what is that point out there in the distant future? Is that point a homogeneous? Is it homogenizing the information that's out there by simply eating its own tail? You know, it's really interesting to think about where we go if what is created and what it's trained on is all the same system. But of course, you could say that about humans, I suppose, as well, because, you know, are we also, you know, where does the creativity, where does the learning completely new strategies come from, even in these systems? So one stimulus would be an edge case that it didn't expect, but then how might it develop completely new strategies for solving the problems rather than learning a strategy? You know, so you learn strategy of going left, going right.
Right.
Maybe there's a better strategy. Who knows what it is? Is that how does that kind of, you know, I don't want to call it creativity, but or innovation? How does that get fed into these algorithms, if at all, or how might you do that?
Right. So, and I think what you're saying is that you probably face a problem that has multiple solutions, right? Mm-hmm. And then based on the multiple solutions, how you pick the best solution.
You may pick a best solution or which seems like a best solution, but there may be another solution out
Correct.
there which is better, for which it hasn't seen yet.
Correct. And that's, yeah, right. So that connects essentially to, I like to go back, maybe you will remember this universal approximation theorem that says, yeah, there exists a neural network that will approximate your relationship, but the question is, how do I find that neural network? It's an existence result. It doesn't tell you how to find it. So then people, again, as I said, very cleverly have come up with this classification of neural networks that will work for, let's say, vision, text, and so on. But if you're starting with something brand new, how do you pick? And if you pick a particular class of, let's say, what I call activation functions, then you might not even get close to the true solution. You might be going in the wrong direction. So it is a hard question to answer. What I would say is that one needs to have the human expertise involved regardless of you know, what we do. And I think that goes back to the guidance question where in order to converge or reduce the time to compute to converge, you need to have some sort of expert example.
Could you imagine building an idiot-proof system with more smarter and smarter idiots out there?
I'm not interested in maybe doing that, but especially if you use federal funds, but we might get in trouble.
So you talked about, you know, in the example of the cruise control, there was a leader and there was a follower. And basically it was a pretty simple system because the leader was leading and the follower was following, and the leader wasn't in any way even conscious, if I can talk about consciousness, conscious of the follower. But in a, you know, you could also imagine a system in which they are conscious of each other, and that another solution is that the leader speeds up rather than the follower slows down. Even more general is the notion that you have an autonomous drone, but actually you have 6 autonomous drones, all with different tasks, all in the same space. How do you kind of generalize in some sense from this kind of simplistic, if even it's not simple, one body issue to multiple bodies?
Yeah, you're talking about how you essentially scale up to the size of agents, if you will, right? One thing that is very good for our approach is that control theory is very modular. So there's something called interconnection theory within control theory that allows you to say, okay, if I have a very large network of, let's say, talk about autonomous electrical vertical takeoff and landing planes that we're probably going to see in the near future, right? Now, if I have this network of eVTOLs that are trying to do essentially take people from place to place, how do I actually have this network interact with the commercial space of aircraft and also the private pilots and then the jetliners and all that? So that needs to be an interconnected system. So you need to be able to transfer information from one system to the other. Now imagine that you want to solve the whole problem using a computation-based approach, like an AI approach. It doesn't scale unless you have a modular theory, which to my understanding is not very well developed yet. So my answer to that is you need to have a theory that allows, or a procedure that allows you to have this large scale and grow the number of agents as they come in. So in the context of adaptive cruise control or cruise control on its own, there is a whole community on platooning. And it's very interesting. This goes back to what is called a string theory, that if you have a large number of cars on a lane, the small errors between two cars at the front can create a huge wave of uncertainty at the back. So it's definitely a very important problem, and one needs to design it with scalability in mind. That's the next step. And I think AI needs to become scalable.
Yeah, so there are a bunch of concerns in terms of how does machine learning-based AI handles edge case conditions or out of the norm environments. So even when learning from experts, the experts themselves might have some holes in their knowledge, and then the AI might be capturing those holes in the knowledge and everything related to that. So I think the question here is, how do you think, and if it's possible, the machine learning-based AI or the current AI is able to handle those conditions, or even if that's the right tool, or maybe some other tools that you might have talked about today are actually the right tools to handle edge cases instead of AI. I guess
Right.
connecting to what you call formal guarantees.
Right. So you could probably solve a problem with multiple, I would say, back to this picture, you might not have one AI algorithm. You might have a bank, many of those AI algorithms, and each of them may be designed to cope with a particular condition. Maybe one of them is the nominal condition. Maybe another one is for takeoff. The other one is for landing. The other one is for level flight. The other one is for avoiding head-to-head collision, right? So even if you can do that, which might be scalable, because now you're breaking up the problem into little pieces, you divide and conquer it. Now the question is, how do you orchestrate between this? So you need to have some sort of systematic way to pick the right control algorithm as you move along, right? What you see right here is what the hybrid approach allows you. This scales to multiple algorithms, and what we call supervisor is a logic that says, okay, among these algorithms, which one should I use? Maybe this one because of the current conditions. But now if I want to switch, let's switch without chattering, right? We saw chattering wasn't good, and let's use this other one in the other condition. And that's kind of the approach that I will call be useful here will be the supervisory-based control with multiple AI algorithms that are being designed for different cases. Now, in order to identify edge conditions or edge cases, you need to design your experiments very well. That's a discipline on its own, design of experiments to actually find these corner conditions, right? Stalling an airplane is very clear. Colliding between two cars is very clear, but what about other situations, right? So that's a whole important topic to include here in the training, right?
So even when people are flying with instructors in planes, they crash. They do crash. I'm just saying, even instructors.
Well, I mean, the crash
that happens.
The crash in DC a few months ago. So unfortunately, that's one case, right? And you can see what happened there. But
that's right.
Definitely, we need to have more safety critical systems active whenever we fly.
Your comments are insanely relevant to the question I was going to pose about the fidelity of input data. And in some ways, that collision is one in which one of the hypotheses being the altimeter may be off in the helicopter that collided with the plane. but I've thought of it from my background in image processing and in facial recognition, where you have training issues where if you use one population of people, you may be error prone in another population of people. And that has been recorded. But then you have a fundamental problem in that there's a darkly colored sheet back there for a reason. It doesn't reflect light. So now the fidelity of your input data for training on certain faces is going to get, in a similar lighting condition, high quality results in the image, but in other situations, not enough light reflects off. And have you guys looked or think about the effects of how do you control for fidelity of that input data?
That's a very good question. One thing we've been doing is how, in the context of fidelity, how do I design my model, let's say, of my aircraft, so that my computations go fast, right? And that's fidelity is important because you can have a very detailed model of your aircraft, but that will be high dimensional, meaning you have a lot of variables. But if you now want to get away with a faster computation time, then you can reduce the dimension. However, when the vehicle gets closer to an obstacle, you better use the high fidelity model, right? Because now you might probably think that this is not going to crash, right? So related to your face expression or face recognition problems, I 100% realize that, you know, those situations will give you false positives, right? Or false negatives, right? And what I would say is that, well, let's think about how does AI recognize image features in images? Well, it has a huge database of labeled images, right? There's an apple and there is a tag that says apple. There is a banana tag, there is banana. And then, you know, we will compare to those references. That's all it does, right? There is no magic behind it. So when your data set is poor, then you're going to probably call a banana an apple when they're around, right? So there is an issue there on the separation between the different features and being able to recognize it with a basic threshold, which is all that they do, is a thresholding, maybe a well-designed threshold. But the answer to that question is, well, you need better data, you need more time to compute and classify, and your network is going to grow. But as we see, in some problems, this is fascinating, right? I mean, writing text or writing emails, or it's just amazing how it works, right? For things that are more dynamic and more complex, three-dimensional, that is the state-of-the-art challenge, right?
Okay. Well, I think this is a good time to end tonight, and I will hand it back to George. Thank you very much, Ricardo. Thank you.
Thank you very much, Ricardo and Alex, for that wonderful conversation. And thank you all for joining us tonight. I hope you'll return on April 16th, where we'll be having a lecture on human-centered AI for computational experiences with Professor Maggie Seyfield El Nasser. Good night, everyone.